Class 11th Chemistry, we were discussing Unit 2 Structure of Atom. In this video, we will discuss about energies of orbitals, filling of orbitals in atom, Aufbau Principle, Pauli Exclusion Principle, Hund's Rule of Maximum Multiplicity, and N plus L rule. First come to energies of orbitals in hydrogen atom. As hydrogen atom has only one electron, that's why this is also known as uni-electron system or one electron system. The energy of an electron in a hydrogen atom is determined only by the principal quantum number. As the principal quantum number increases, energy is also increases. Thus, the energy of the orbitals in hydrogen atom increases as follows. Lowest energy 1s. Then 2s and 2p have same energy but greater than 1s. Then 3s, 3p, 3d have same energy but greater than second energy level. Okay, in the same way 4s, 4p, 4d, 4f have same energy but greater than third energy level or third shell. The orbitals having the same energy are called degenerate orbitals. The 1s orbital in hydrogen atom corresponds to the most stable condition and is called the ground state. And an electron residing in this orbital is most strongly held by the nucleus. An electron in the 2s, 2p or higher orbitals in a hydrogen atom is in excited state. And the energy of these orbitals can be represented like this. This is an energy level diagram. This represents increasing order of energy. Lowest energy for 1s, then 2s and 2p have higher energy than 1s, but 2s and 2p have same energy. In the same way, this is 3s, 3p, 3d have same energy but greater than this second cell. This energy level diagram for hydrogen atom can also be represented like this. This is again increasing order. This is lowest energy 1s which is present in the first shell. In the second cell 2s and 2p subcells are present which have higher energy than first cell. In the same way third cell has higher energy than second cell. Fourth cell has higher energy than third cell. But the subcells and orbitals present in a particular cell all have the same energy. The energy of an electron in a multi-electron atom. Multi-electron means more than one electron. The energy of an electron in a multi-electron atom depends not only on its principal quantum number, that is shell, but also on its azimuthal quantum number, that is subcell. That is, for a given principal quantum number, S, P, D, F all have different energies. The main reason for having different energies of the subcells is the mutual repulsion among the electrons in multi-electron atoms. Shielding effect. Due to the presence of electrons in the inner shells, the electron in the outer shell will not experience the full positive charge of the nucleus, and this full positive charge of the nucleus is represented as Ze. The effect will be lowered due to the partial screening of positive charge on the nucleus by the inner shell electrons, and this is known as shielding effect. The net positive charge experienced by the outer electrons is known as effective nuclear charge, and this is represented like this ZeFF. Okay, and this is E, effective nuclear charge. The energy of various orbitals or various subcells is determined by the N plus L rule. Now, what is its statement? The lower the value of N plus L for an orbital, the lower is its energy. If two orbitals have the same value of N plus L, the orbital with the lower value of N will have the lower energy. We can explain like this. In this, orbitals or subcells are represented. This is 1s present in first energy level or first shell. This is 2s and 2p subcells in the second cell, 3s, 3p, 3d subcells in the third cell, 4s, 4p, 4d, 4f, these are present in the fourth cell. And in the same way, this is 5s, 5p, 5d, 5f are present in the fifth cell. Value of n. How can we see value of n? This number, this 1 or this is 2, this is 2, this is 3, this is 3. These number represents the value of n for a particular subcell. In this way we can say for 1s value of n is 1, for 2s this is 2, for 2p this is 2, for 3s this is 3, 3p this is 3, 3d again 3. Then this is all the 4s, 4p, 4d, 4f have value of n equal to 4. Okay, in the same way these 5s, 5p, 5d and 5f have value of n equal to 5, and 6s the value of n is 6. Then value of L. How can we determine the value of L? We have discussed about the quantum number, azimuthal quantum number. If S subcell is there, value of L is always 0. For P subcell, value of L is 1. For D subcell, value of L is 2. For F subcell, value of L is 3. Okay. Whatever the cell in which these subcells are present, we will decide the value of these subcells like this. We can say this is 1s, value of L is 0, 2s, value of L is 0. Okay. For 2p, this is 1, 3s 0, 3p 1, 3d 2. This is again 4s 0, 4p 1, 4d 2, 4f 3, 5s 0, 5p 1, 5d 2, 5f 3, 6s 0. This is the value of n. Then if we add value of n and value of n, we will get the n plus L. And these values are like this: 1, 2, 3, 3, 4, 5, 4, 5. This is 6, 7, 5, 6, 7, 8, 6. Okay. Then on the basis of this n plus L rule, we can arrange these orbitals or subcells in the increasing order of energy by comparing their value of n plus L. Lower value of n plus L means lower energy. If two subcells or two orbitals have the same value of n plus L, then orbital with lower value of n will have the lower energy. Now see this increasing order of energies. 1s lowest energy, then 2s and 2p. Again see, this is 2s and 2p, both have the n value 2. Okay, but we have to see value of n plus L. Again see, n plus L for 2s is 2 and n plus L for 2p is 3. That's why 2s has lower energy, 2p has higher energy. In the same way, next energy level is, this is 3s, then this is 3p. Okay, then after 3p, 3d has n plus L equal to 5, but 4s has n plus L equal to 4. That's why 4s subcell has lower energy than 3d. Okay, that's why this is 4s, and after 4s this will come to 3d. Okay, after this 3d you can say this is 4p. Then after 4p, which orbital or which subcell will come? That is 4p has the n plus L value equal to 5. Then we can say this is again 5s. Then after 4p, this is 5s. Then after 5s, this is 4d. And after 4d, that is this is 5p. Okay, and after 5p this will come to 6s, and after 6s this 4f will come. Okay, in this way we can arrange these orbitals in the increasing order of energies. Energies of the orbitals in the same subshell increase with the increase in atomic number. For example, energy of 2s orbital of hydrogen atom is greater than that of 2s orbital of lithium. Okay. See, orbitals in the same subshell decrease with increase in the atomic number. This is 2s in hydrogen atom and this is 2s in lithium. Okay, but for lithium atomic number is greater than hydrogen. That's why the 2s orbital in lithium has lower energy. Is it clear? In the same way, sodium and so on. We can say that is for 2s orbital of hydrogen has the highest energy, then 2s of lithium, then 2s of sodium, and then 2s of potassium. As the atomic number increases, energy of the orbitals in the same subshell decreases. Clear? This is again energy level diagram for multi-electron atoms. In two way you can represent. This is the one way and this is the another way. This is 1s, lowest energy level. Then this is 2s. Then these 2p orbitals present in the 2p subshell. Okay. Then this is 3s. Then 3p. This is 4s. Okay. And after 4s, this is 3d. And after 3d, this is 4p. And so on. One thing you have to note down. As the value of principal quantum number increases, okay, as we go from this through this, the energy gap between these two levels is decreases. Energy gap, you can say this is between 1s and 2s with a large energy gap, but 2s and 2p, this energy gap is less than this is 1s and 2s. Again, this energy gap between 3s and 2p is less than 2s and 2p, and so on. Okay. Filling of orbitals in atom. The filling of electrons into the orbitals of different atoms takes place according to the Aufbau Principle, which is based on the Pauli's Exclusion Principle, Hund's rule of maximum multiplicity, and the relative energies of the orbitals, that is N plus L rule. Now, what is this Aufbau Principle? In the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, the electrons must occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. This is called Aufbau Principle. And relative energies of these orbitals are determined by the N plus L rule, which we have discussed already. With the help of this diagram, we can also determine the increasing energy of the orbitals in a multi-electron atom. Okay, you can say this is 1s. Then you can say this is 2s and 2p orbitals or subshells of the second shell. This is 3s, 3p, 3d. These are the subshells in third shell. This is 4s, 4p, 4d, 4f subshells of the fourth shell. We have arranged like this. Okay. Now, if we go from this side, this to this, lowest energy is for 1s. Okay. Then again you move back side. Then after 1s, 2s will come. Then after 2s, this will come to 2p. And after 2p, this is 3s. After 3s, this is 3p. After 3p, this is 4s. And after 4s, electron will go in 3d. After 3d, 4p, then 5s. Then after 5s, 4d, this is 5p, this is 6s. And then after 6s, 4f, then 5d, this is 6p, 7s, and after 7s, this is 5f, 6d, 7p, and 8s, and so on. This is according to the N plus L rule. This is the one way to remember the order of increasing energies of the orbitals. Is it clear? Pauli exclusion principle. No two electrons in an atom can have the same set of 4 quantum numbers. Okay. This can also be stated as only 2 electrons may exist in the same orbital and these electrons must have opposite spin. This means that the 2 electrons can have the same value of 3 quantum numbers N, L and Ml, but must have the opposite spin quantum number. Okay. See example, hydrogen, atomic number is 1. Its electronic configuration is written as 1s1. If we write all quantum numbers for this electron, then we can write N is equal to 1. This one is coming from this. L is equal to 0. Why this is 0? This is for as subcell value of L is 0. Okay. Then this 1s subcell has one orbital and that is also the 1s, and for this orbital the value of ml is 0 and ms either it may be plus half or it may be minus half. Out of these two, one is only possible. That's why we can see this for one electron present in the hydrogen atom, the 4 quantum numbers are n is 1, l is 0, ml is 0, ms is either plus half or minus half. Now, if we go to the helium, atomic number is 2, its electronic configuration is 1s2. Now, in this case, 2 electrons are present in the 1s subcell. Now, if we write the set of quantum numbers for first electron of helium, then we can write n is equal to 1, l is equal to 0, ml is equal to 0, ms is plus half. Then the set of quantum number for the second electron, n is equal to 1, l is equal to 0, ml is equal to 0 and ms will definitely minus half, it will not be plus half. Is it clear? Because according to the Pauli's rule, thus if 2 electrons are present in orbital, then they must have opposite spins. Okay, then we can say if one electron has plus half spin quantum number, then another electron will have minus half spin quantum number. Okay, that's why if we compare this set with this one, then we can say that is both the set are not same. There is difference in this spin quantum number. Next, if L is equal, next example is lithium. If Z is equal to 3, then definitely third electron will go into the next energy level. That is after 1s, electron will go into 2s. Okay, that's why electronic configuration of lithium become 1s2, 2s1. This is Pauli exclusion principle. Hund's rule of maximum multiplicity. Pairing of electrons in the orbitals belonging to the same subcell P, D or F does not take place until each orbital belonging to that subcell has got 1 electron each. That is, it is singly occupied. You can say that is P subcell has 3 orbitals, D subcell has 5 orbitals, F subcell has 7 orbitals. Okay, if we take the example of this one, in this case 3 orbitals are there. First of all, each orbital will occupy single electron. Then pairing will start with the help of one example. Nitrogen, atomic number is 7. Its electronic configuration is 1s2, 2s2, 2p3. Now these 3 electrons in p subcells are distributed. How? 2 ways are there. There are the 3 orbitals are there. Each orbital will occupy single electron. This one and all these are with same spin. Another way is that is 2 electrons are in one orbital. Second orbital has 1 electron and this is third is empty. That's, we can say this is incorrect configuration while this is correct configuration. Because first of all, each orbital will occupy single electron, then only pairing will start. Okay. Now if we come to the oxygen, atomic number is 8. Okay. Now electronic configuration is 1s2, 2s2, 2p4. Now first, in case of 2p subshell, first of all one electron will come in each orbital, then fourth electron will get paired. That's why this is correct electronic configuration. Now in this case, this is vacant. Okay, and these are paired. This is not possible according to this rule. That's why this is incorrect configuration. Okay, subscribe my channel to get the new videos. Thank you.